Thanks, everyone. So my name is Kehinde Babaagba. I'm a PhD researcher at Edinburgh Napier University. I'm supervised by Thomas Tan and Emma Hart, and I'll be presenting our work, automatic generation of adversarial metamorphic malware using Mapolite. So I'll first introduce what a metamorphic malware is. So a metamorphic malware refers to malwares that changes the signature at each execution. It changes its entire code between generations as well. And it often uses a number of obfuscation techniques to make it hard to reverse engineer, and it works by hiding its instruction code in the host machine's program code. So they often go undetected. They evade detection rather from a number of antivirus engines, because these engines are trained, to recognize specific variants of malwares. So these malwares often use a number of mutation techniques, which include techniques like variable substitution, which involves, replacing a variable with a valid one without changing the behavior of the program code. Others include instruction reordering, which involves altering the flow of instruction without changing the behavior of the program code. Garbage code insertion involves adding junk codes without changing the meaning or the behavior of the program code, among other mutation techniques. So because of the complexity of this class of malwares, it's often hard to train machine learning techniques on them, because we don't really know where these malware will morph to, so most of these machine learning models do not generalize. So for us, it's actually desirable for us to search for and find as many as possible a set of variants that are also diverse, so that machine learning models can learn from this set and to improve, most of these detection models, so as much as possible, we want that the variants are as diverse as possible, and this is to ensure that that model generality is improved. So essentially, the goal of this paper, of our work, is to search for new variants that we can use in the future to train machine learning models. And we want to make sure that the variants that we create are as diverse as possible, as well as large as possible. And in order to ensure that they are diverse, we use equality diversity algorithm. In particular, we use Mapolite. And Mapolite is designed to generate a repertoire of variants, and that these variants are diverse with respect to some features. And I'll be explaining Mapolite in later slides. So in this research, we have basically two research questions. The first one is, how does diversity of samples produced by running Mapolite's algorithm compare to running repeated execution of a standard evolutionary algorithm, and which we refer to as mal-EA. And we'll be describing that algorithm in the later slides. And also, how does the evasiveness of samples produced by Mapolite also compare to repeated execution of a standard evolutionary algorithm? So now we'll be talking about Mapolite in general. So Mapolite belongs to a raft of new, evolutionary algorithms that are actually called quality diversity algorithms, and they comprise of algorithms like novelty search with local competition, Mapolite, among others. And these algorithms have only recently emerged, and the aim of the quality diversity algorithm is actually to fill a space of possibilities, with the best possible example of each type of achievable behavior. So what happens is that with this type of algorithms, we return a new archive of solutions that are high quality and that are also very diverse, in a single run. And Mapolite falls into the category of quality diversity algorithms. So for Mapolite, what it does is it actually traverses a high dimensional search space. So what it tries to find the best point in that search space, of the feature space with low dimension, and the features are usually defined by the user. So if you have an objective function and you have a set of features, so what Mapolite does is it finds the best possible solution for each combination of features, of possible combination of feature values. So, and would be given an instance of the application of Mapolite in the following slide. So this is an example of the application of mapolites in evolutionary robotics, and it shows how we can drive structural diversity in soft robots using mapolites. And in this case, we have the objective function, which is often called, performance criteria or quality objective, depending on what you want to call it. What it in this instance is the distance covered by the soft robot, in 10 simulated seconds. And we see the features of interest there to actually two features. So the first one is the percentage of voxels that are stiff bone material, and the other feature of interest is the percentage of voxels, that are filled. And we see how in this instance, mapolites adapts a design theme, along the desired dimension of variation, and we can actually see that it actually paints an overall picture of the performance capabilities, of each region of the feature space. And in this instance, for instance, we can see that the yellow are the regions with higher performing solutions than the blue. Now we go to a standard version of mapolite. So this is just a standard version of mapolite, and mapolite would begin with random solutions, then you use a variation operator, and then to the solutions, and then you would calculate the feature description of the variance. So, it depends on the feature of interest of, your choice. Then you also calculate the performance of the variance. Then you place the new variant in a corresponding cell of a map based on its feature descriptor. So as long as it is better than the current occupant of that cell. So, we adapt this algorithm with our own variation operators, our performance criteria and feature descriptors, which we'll be discussing in the next slide. So mapolite begins with, a single quality objective. You define your features of interest and map it to a discretized grid. Then you generate multiple solutions, one for each pair of features, and you find the best solution for each cell. So when you generate your initial solutions at random, you usually calculate the feature vector, you map to an archive, and you only store one solution per cell. So that's the elite, that's the best solution and that is found so far based on the objective function, as we can see from the slide. Then until you finish, you select a random genome, you copy and you apply a variation operator, and you evaluate and place it in the grid if it's elite, as we said. So it only replaces the current occupant of the cell if it is better. Otherwise, you discard it, and you repeat this until you finish. So we see that by shading using the objective quality or the objective function, it eliminates the search space, hence why mapolite is usually referred to as a quality diversity algorithm. So in order for us to explain how we use the mapolite, we actually just want to give an explanation of our system framework. So as we can see, we start with an original malware, which is it's an APK, and we reverse engineer them using an APK tool that we decompile it to a SMARLI. And the reason why we choose a SMARLI is because it's easily modified by an EE. So we mutate that, and then the mutated SMARLIs form the population of, the evolutionary algorithm, and it follows the normal process of, selection and mutation. Another thing we do is that after we mutate the parent, we recompile it, and we ensure that it's still executable, and that means it compiles and it runs, and then we evaluate it and replace it if it's better than the worst solution in the population. One important thing we also check to see is that it's malicious. So if the APK retains its malicious nature, we keep it in a data store of malicious APKs, else we keep it in a data store of benign APKs. So in our case, in our problem space, what we are the features that we are interested in are, we want to ensure that the variants are structurally and as behaviorally dissimilar from the original malware as possible. Hence, our features of interest are structural similarity and behavioral similarity, which we'll be explaining in the next slide. So the first is to structural similarity. So we want to ensure that the original malware and the variants are structurally dissimilar as possible, and we use a number of code level and text-based similarity metrics, as we can see from the slide. And so the metric returns a value between 0 and 1, where 0 means that the the mutant and the original malware are completely dissimilar, and one means that they are the same. And also for the behavioral similarity, it also measures the behavioral similarity between the original Smalley, the original Smalley and the mutant. And we usually collect the behavior by studying monitoring the behavior of the mutants using S-trace, and we simulate user interaction using monkey runner. So when we collect the behavior, we store it in a log, and this is converted to a system called vector, which is given in the slide, and which each element of the system call vector corresponds to the frequency of each of the system calls made. So that means we have the vector for the original mutant, the original malware, sorry, and then the mutant, and then the behavioral similarity, we just calculated as the cosine similarity between the system call vectors. Of course, again, it returns a value between 0 and 1. 0 means that they are completely behaviorally dissimilar, and 1 means they are behaviorally the same. And it's important to see that because we're trying to ensure that the similarity, both structural and behavioral similarity, are as similar as possible, meaning that we prefer the value ideally to be 0. So it's, for our case, it's a minimization problem. So as earlier said, while using Mapillity, you need to define your fitness evaluation. Is often called, it can be called quality objective, or what is like your performance criterion. And in this case, our fitness measures the detection rate. That's the percentage of the 63 antivirus engines employed that fail to detect a particular mutant. And where the detection rate is 0, it means that no engine detected that variant, and 1 means that all the engines detected that mutant. Thus, our problem is treated as a minimization problem. So the next step for the Mapillity is the variation step, and we just select an operator randomly from the mutation operators that I'll be explaining in the next slides. So first mutation operator is instruction reordering. So this introduces a go tool that jumps to a label that does nothing. Then we have garbage code insertion that inserts junk codes like line numbers that do not actually affect the behavior of the code. And variable swapping replaces variables with valid ones while ensuring consistency with the variable names and doesn't change the behavior of the code. Then, if you recall from the research questions, we say that we compare Mapillity with malEA. So we'll just briefly explain malEA. The details of malEA is in the paper given at the bottom of the slide, if you can see it. So malEA uses, the same mutation operators and uses tournament selection. It uses no crossover, and the fitness function is a weighted sum of 3 values. It checks also for the evasiveness of the mutants, the behavioral and the structural similarity between the original malware and the mutants, and it tries to encourage a search for evasive yet dissimilar solutions. And we would find that the full details of the paper is given in the reference at the bottom of the slide. So now we collect data from 3 families, and we get them from 2 popular malware dumps, mobile malware dumps, and they are malgenome and contagio. And we select the families based on their malicious payload. So we have 3 families: Dugalik, DroidConfo, and MGG Tracker. While Dugalik is known for stealing personal information from mobile phone users' accounts, DroidConfo is known for escalating privilege and gaining remote control of mobile phone users' accounts, and MGG Tracker is known for incurring financial charges to mobile phone users. So now we compare Mapillity with malEA. So in terms of the settings, we ensure that both Mapillity and malEA we use the same parameter settings. So in terms of mutation rates, number of iteration, and population size, we maintain the same values. And for selection, for the malEA, we use tournament selection, while for Mapillity, we use random selection. And then we compare the malEA and Mapillity using standard algorithm performance metrics, global performance, coverage, reliability, and precision. So while global performance computes for each run the fitness of the single best performing solution divided by the fitness of the best solution possible, we see that coverage measures how many cells of the feature space a run of the algorithm is able to fill, of the total number that is possible to fill. Then we see that the reliability metrics measures for each one the closeness of the best solution found for each cell to the best possible performance for that cell, and that's averaged across the whole map. And precision is it's similar to reliability, but for a single one, it averages only the performance of cells that were built for that one, and it generally provides an indication of how high performing a solution is relative to what is possible for that cell. So we do the comparison for the three malware families we said as to Zhiyuan, and Thread Control. And so this is the qualitative comparison of the three families of malware. So the first one is Zhiyuan. So the X and the Y axis are defined based on our features of interest. So S of X refers to structural similarity. ES of X also refers to behavioral similarity, which we explained before. And the goal is to it's a minimization problem, so we want to reduce those values. And the color bar refers to the detection rate, and obviously we want to reduce those values too. Ideally, we want to provide the lower the value, the better for us. So lighter regions are better than the darker red. So that means lighter region is better than darker red. So we can see for the Zhiyuan family that multi-A covers a very covers sparsely the search space as opposed to the map rather, as opposed to MapLead. We see MapEA sparsely occupies only 12 cells actually, whereas MapLead covers 50 cells, which shows that it's more evenly distributed along the range of each feature, as we can see, and there's more diversity. For the Droid Kung Fu family, we see similar observation. We see that MalEA occupies 14 cells, and we see that MapLead occupies 44 cells, and we see that although we can see that in terms of the range of the structural similarity features, we see that it extends more widely in MalEA than MapLead, but we see that the solutions that MapLead finds are more distributed consistently across the range. Then for GD tracker, we see that MapLead also generates a larger archive of solutions, and we see that for both the structural and behavioral similarity features, it extends more widely with MapLead than with MapEA. And MapEA occupies only 14 cells, while MapLead occupies 8 cells. So the next slide does a quantitative comparison of both algorithms for the three families. So we see that it's actually the greater detail is found in the paper. So we just explained this quantitative comparison briefly. So the table provided gives us the fitness of the best, mean, and worst variants produced by both algorithms, and the fitness, as we said, it's detection rate. So that's the percentage of detectors that recognize that the variants are malicious. So if a value of 0 represents a failure of all 63 vectors. So smaller is better in this instance. So as we can see from the table, we see that both algorithms produce variants that are more evasive than the original malware for three classes of families. But we can see for Zhiyuan, for instance, we see that the variants that are produced are detected by 28% of the detectors, and while for Droid Kung Fu, we see that for the Zhiyuan, that's 28% of detectors for both algorithms. For Droid Kung Fu, however, we see that EA produces a single variant that is only detected by 6% of the detectors, outperforming MapLead, in which a single variant is detected by 18%. For GD tracker, EA produces a single variant that is only detected by 27% of the detection engines. And although we see that it outperforms MapLead, in which a single best variant is detected by 29% of the engines. So we see that the median values are similar for Zhiyuan and Droid Kung Fu, but we see for GD tracker, the median value for MapLead is better than, is better for MapLead than MapEA. And the worst variants produced by MapLead is more invasive than the worst produced by MapLead for the three classes of families that we covered. And then, still talking about the quantitative comparison of both algorithms, for the three families. But the Gallic family, we see that for Mapulid, it does better than MAPEA, in terms of global performance, in terms of coverage, in terms of reliability, and you can see that it performs similar. They have similar performance in terms of precision for both MAPEA and MAPEA for the Gallic family. For Droid Control family, again, we see that of course MAPEA does better than MAPEA for coverage and reliability, and very closely for global performance. In terms of the precision metric, you see that. However, it's MAPEA performs MAPEA. For the GG tracker family, we see that MAPEA does better than MAPEA in terms of global performance, in terms of coverage and reliability, and it performs closely for precision. And you can get the exact details of the use of the experimentation in the paper. So the last analysis we actually do is, which I won't be spending so much time on because I know I don't really have as much time. It's just an analysis of the detection engines. So we do it to see what engines are more susceptible to the mutants, the potentially mutated versions of the original malware, and so we determine the percentage of evolved malware that a detector fails to recognize, and we only consider the engines which recognize the original malware. So in order to just understand how vulnerable potential mutants remain to potential mutants are, and how much do they remain capable of detecting the mutants that we create. And so it's important to know that the longer the balance, the worse the antivirus engine. So we just take one instance, and so that is Droid Control, and we see that 4 of the 21 engines that detected the original malware were also able to detect all the evolved mutants, and we have examples like Avast Mobile, Avira engines, and those engines actually proved robust to the Dugali mutants as well. And we see that 3 of the 24 engines have failed to recognize all of the evolved. 3 of the 21 engines actually failed to recognize all of the evolved mutants. And we see examples like Aegis Lab, Dr. Weber, McAfee, GW. And it's important to note, although I don't show the analysis for Dugali and GB Tracker, you can find the details in the paper. But we can notice that McAfee GW engine appears vulnerable to the Dugali and Droid Control family. And then Avira proved 100% robust to all the families of malware mutants that we consider. So in conclusion, we have been able to show that quality diversity algorithms are very well suited to our problem domain, and I mean, to the best of our knowledge, we've not seen any application of quality diversity algorithms in cybersecurity domain, and they are because we feel that quality diversity are suited because they're designed to return, an archive of solutions that are not just large set, but they are also diverse and high quality. So we have shown that the repertoire returned by MAPEA outperforms that returned by, MALEA in terms of diversity and the size of the repertoire. And both methods produce very considerably more evasive than the original malware. So of course, there's still room for improvement. We can investigate other things like the appropriate size to use. We can run the algorithm for longer, to see if it improves the coverage. But we know that quality diversity algorithms are a good avenue for exploration in the field, particularly if it is, combined in the setting of generative adversarial network where improvements in, the samples generated drives improvement in the detection methods and, the other way around. So we're also currently working on using the variants that we get from MALE and from running MALE and MAPEA to serve as training data to improve machine learning models. So thank you. Any questions? Thank you for listening.
Okay, thank you very much, Kehinde. I forgot to say that your paper is also nominated as Outstanding Student Award. So cross your fingers. Maybe you tomorrow we'll see if you are the winner. But before we finish this session, is there any Any question for Kehinde? No one? Okay, I have a question. How to deal is a every licensing issue about using the antivirus and malware detection engines? You have to pay something or
So
sign some contract?
Yeah, so in order to gain access to, so we use Virus Total, which comprises of a suite of antivirus engines. So you would usually have to contact them, then you would sign in, but the process is completely free, and then we give you a unique ID which you use to run your experiments.
That's great. That's great. Good to know.
Yeah.
Good to know.
Yeah.
And what about time execution? Do you need a lot of time to execute all this stuff or something like that? Use a cluster of we can do this in our personal computers.
So at the moment we run it in a virtual machine, but on a personal computer. So so you notice that we run the algorithms for just 120 iterations because computationally expensive. So at the moment we actually focus on the quality of the solutions that we provide as opposed to time it. So so probably if you can use maybe like a 50 or 60 data one, probably you want the algorithms for longer, and kind of hopefully find them that are more interesting.
I'm sorry, could you move your mic? Because I can hear you very well.
Oh, okay. Can you hear me now?
Okay, much better, much better.
Okay. So like I was saying, no, so I just said that we run the algorithm actually just on like a personal computer, in a virtual environment. But we do not use any we do not, we don't use like any GPU or anything like that. So we're actually just focused on the quality of the solutions at the moment, not necessarily the computational time, and although we know it's computationally expensive, and sometime in the future we can use our experiments using GPU or GPU, at a later point, and hopefully we'll, get better results, because we can run the algorithm longer. So if you notice, we run it for only 120 iterations, and the algorithm for both, algorithms. So we can increase that, depending on how much computational stuff we have in the future. But at the moment, we're just working with what we have, and we're focusing on the quality of the solutions regardless of the time of it.
Okay. Anybody else that wants to ask something? Okay, thank you very much for your work. Virtual clap from all of us, and congratulations. Very nice work. Okay, so these sessions are already finished. Remember that in a few minutes, the poster rooms will be opened. There is a link in the EvoStar webpage to directly access to the poster you are most interested on. And thank you very much to our presenters, and thank you all to our attendees. Hope you enjoy the rest of the conference, and see you later.